There we go. We tend to memorise your perfect squares and so that and those sort of things, but really cubics are just as important. There's a plus b all cubed turns out to be a cubed plus 3a squared b plus 3ab squared plus b cubed. Lovely pattern you'll notice there. Right? The powers of a are going down by 1, powers of b are going up by 1, coefficients go 1, 3, 3, 1. So there's a lovely symmetry to the whole thing. The minus one's very similar, it's just that the plus and minus alternate. So it'll be minus 3a squared b and the minus b cubed. Okay. The difference of two cubes starts out a minus b, then in the other one a squared plus ab plus b squared. That is why I said yesterday with the difference of two squares, I start with a minus b, because it's consistent, you'll notice. Difference of two cubes also starts with a minus b. If I wanted to do the difference of two quartics, it would start with a minus b, and so on and so on and so on. And then in the second one, you get, again, a lovely pattern. Powers of A going down by 1, powers of B going up by 1. The coefficient for this one is always 1. The big mistake is people put 2ab there because we're so used to seeing a squared plus 2ab plus b squared. But the coefficients are all 1. We also have, though, the sum of two cubes. Okay? We don't have the sum of two squares. That doesn't factorise nicely. Well, not using real numbers anyway. It starts with a plus b. But notice the similarity. So all I've got to remember is I start with what I got. So if it's a minus, I start with a minus. If it's a plus, I start with a plus. The actual pronumeral part of the terms is identical. A squared's going down by 1, b squared's going up by 1. Well, if I had a minus here, it's a plus there. If I had a plus here, it's a minus there. So really it's the same formula, but you know, the plus and minuses are around. So 2a minus 5 all cubed, then, well, depending on how much you can handle in one hit, you might write it out once we start getting above squares. But again, it possibly is something you do in your head. You know, first term cubed, then 3, power goes down by 1, power goes up by 1. So the first term now is squared, second term's now. Notice the two powers are always adding up to be 3. Okay? So that's how you can always keep a check on yourself. So if this is the power of 2, 5 must be to the power of 1. 2a is to the power of 1, 5 must be to the power of 2. And then we keep going on the pattern. So now we're at where 2a is to the power of 0, which is 1, so we don't write it down. 5 is to the power of 3. It was a minus, so the signs are alternating. And just tidying it up, there we go. Nothing adds together there. There's our expansion. X cubed plus 8, so that's the sum of two cubes. 8, of course, is 2 cubed. So x cubed plus 2 cubed, again, you might just think that, and you wouldn't necessarily write it down. So it starts with x plus 2. Powers of x will go down by 1. Powers of 2 will go up by 1. So x squared minus 2x plus 4 in the second parentheses. Y cubed minus 27a cubed is different to 2 cubed because 27, of course, is 3 cubed. So it is 3a all cubed. So it will start with y minus 3a. Powers of y will go down by 1. So y squared, then the powers of 3a will go up by 1. So we have 3a times y, and then 3a all squared in the second one. In fact, we can generalise this. A to the n minus b to the n will always start with a minus b, and then the powers of a will go down by 1, the powers of b will go up by 1. The two powers will always add to give n. Okay? So that's a factorisation of a to the n minus b to the n. A to the n plus b to the n only works for, say it right, odd. Yes, I was make sure I must say the right word. Odd numbers. It's why we don't have sum of two squares. We do sum of two cubes. We don't have sum of two power of 4s. We do power of 5s and so on. And in that case, the second one, this would start with plus b. The second one, the signs would alternate. Plus minus, plus minus. Because what you're really doing, I suppose, with the odd power is for b, you're substituting in negative b. And negative b to the power of n is always negative b to the power of n, and you get minus minus becomes a plus. Does that make sense, or did I say that too quick? Right? What I'm saying is, it really is the same formula, but you're saying a to the n minus b to the power of n. And minus b to the power of n is minus b to the power of n. Okay, raise a negative to an odd power. That's if n is odd. Raise b to an odd power, it's going to be negative. And so the minus minus becomes plus. So thus we can get a formula, because what we're then saying is, it's a minus b, a plus b, and that then explains why every second one is negative, because every second one, the power of b is an odd number, and the negative number to the odd power gives me a negative number. Okay? Square, I can't do it, because of course negative b to a even power is just b to the even power. So I can't create the a to the n plus the b to the n for an even power using real numbers. So if I had x to the 5 minus y to the 5, then it would be x minus y, powers of x go down by 1, powers of y go up by 1, all the way down, and there it is. It does factorise further, by the way, because every polynomial can be factorised down to be a combination of linear and quadratic factors. Some quadratics won't factorise, but everything can factorise down to be quadratics and linear. So it must be possible, actually, in this case, to factorise this quartic, because it must be possible to get it down to a combination of linear and quadratic factors. But anyway, we'll just leave it like that. A to the 7 plus 1, as I was saying, it's like the minus minus. So we end up with a plus 1, powers of a go down by 1, powers of 1 go up by 1, but 1 to the power of anything is 1, signs alternate. All right, exercise 1/4 of a jolly good fellow.